Okay, good morning, everybody. Good morning, everybody. Welcome to our science seminar for today. Today we have Dr. David Hilton with us from Baylor University. He's looking for students, graduate students. So if you're interested in the stuff that he's talking about, be sure to talk to him afterwards and join us for lunch as well in the corner cafe. So just let me tell you a little bit about Dr. Hilton. He joined the Baylor faculty in the fall of 2019, just before COVID hit, just in time to shut everything down. Okay, sad time to start something, right? Before that, he was an associate professor of physics at the University of Alabama in Birmingham. Okay. He did his postdoc work for the Center of Integrated Nanotechnology, Los Alamos National Lab, and also did some postdoc work at Rice University. He's got a bachelor's degree from the University of Rochester in New York. He has a master's, and was that physics?
No, Rochester was optics.
Optics, ooh, okay. Master's in optics from the University of Rochester, so he should look really good because he's got a master's in optics, yes. And he has another master's from Cornell. The second master was in
Engineering physics.
Engineering physics, which you have a major in. And he has a PhD, and now your PhD, is that in engineering?
Yes, engineering
That's in
physics.
engineering from Cornell University, okay? So well qualified. He's going to tell us all about exciting things here. And let's give him a warm applause.
Thank you very much for the introduction. So in addition to all of that, I'm also the director of the graduate program. So even if you're not interested in what I'm doing, if you're interested in some of the things that's going on in physics at Baylor, beyond just materials, I'm interested in talking to you as well. So I want to talk a little bit today about designing materials for electronic applications. And talk about some that are novel, and then taking a look at some of the materials that we currently use and getting them to do new things. So if you look at this, our periodic table, how many of you own a cell phone? Computers, all of this type of stuff. You own devices that are based on silicon. The radio inside of that right now is an alloy of silicon and germanium. That's what actually allows your cell phone to connect to the tower. Once the signal gets over to the tower, that signal gets turned into something that's put into an optical fiber and fed over to either the landline that you're talking to or the other cell phone. That's a laser that's indium gallium arsenide phosphide. So we're starting to look at materials as indium, gallium, arsenic, and phosphorus. And so that's the type of laser that you would use to couple the signal onto an optical fiber. But basically, all of your communications on a daily basis are about 5 or 6 atoms here. And so what we want to look at in our area in working with people that grow materials, and then we're spectroscopists, so we're trying to understand how these materials tick, is to learn how to either take new combinations of elements and make new materials that have new applications to them, or in the not so novel part of all of this, take a very common material, which is gallium arsenide. Anyone's ever seen a red laser? Oh wait, right there. That's a gallium arsenide laser right there. And so aluminum, gallium arsenide laser, because that technology is well established and extremely inexpensive. And trying to understand how we might be able to get things out of gallium arsenide that other people haven't been able to get before. So I'm going to talk about a material here, which is gallium bismuth arsenide, and then we're doping it with erbium arsenide nanoislands. I'll talk about why we're doing all of that there. But the interest there is what's coming next with this, and how we're going to be able to send signals out of a cell phone in the future. And then I want to take a look at some 2D gallium arsenide samples and a technique that we use called cyclotron resonance spectroscopy to try and understand how we could use gallium arsenide as the basis of quantum sensing devices and quantum computers in the future. And then if I have time, I want to talk a little bit about some of the high magnetic field work that we're doing in collaboration with the National High Magnetic Field Lab in Tallahassee. And the material I'm going to talk about is another new material, which is molybdenum disulfide. So molybdenum is here on the periodic table, and sulfur is right below oxygen. And so these are materials that people are looking at for next generation electronics. And then I'll kind of wrap up from there. So the technique that we use is called terahertz time domain spectroscopy. So what do? I look at how materials reflect light, and from that I try and understand how they conduct electricity. So the conductivity of a material is the same physical quantity in a material that we call also the dielectric constant or the refractive index, or all of these things that we talk about how if I put an electric field or a magnetic field on a material, how does it respond? So whether it's I'm putting electrodes down and I'm driving a current, that current is the response, or whether I'm taking light, as we do in this case, and driving electrons around based on the electric field of the light and causing phenomena to happen. It's all taking a look at how these materials respond with external stimulus and trying to understand how they were being held together to begin with. So types of experiments we do, I'll go through all of the details of this on a future slide. I start off with a laser system. This laser puts out 1,000 pulses per second, and each of those pulses is 25 to 50 femtoseconds long. Femto, metric prefixes. Anyone want to tell me what a femto is?
Really small.
Really, really small.
15.
10 to the minus 15 seconds, that's right. So a 100,000th of a billionth of a second long. So specifically when you talk about materials, that's the right time scale to be an electron on one atom and move to your neighbor. So at this sort of time scale, when we can look at materials, we can literally watch you guys all move around in seats, in the chairs and all of this. That's the right time scale to be looking at how electrons move at that sort of very granular level in materials. And this is the sort of spectroscopy that we do. For terahertz time domain, so this is a visible light laser. This puts out light at 800 nanometers. We use nonlinear optics to shift that out to the far infrared. So whereas this is a wavelength at 800 nanometers, when I'm done with all of this, I'll be looking at 300 microns to a millimeter in wavelength. Tells us a lot about the material, but that's actually where this is moving to right now. So right now, this is working in the megahertz frequency range and getting up to about a gigahertz. The next generation after this, 6G, we'll talk about it, it's going to be 30 gigahertz to 300 gigahertz to 3 terahertz in some of these ranges. So all of this communications is moving into this range from the electronics side of everything. I'm a laser spectroscopist and I get down to it from higher in frequency. So this is the video. So I was joking with him beforehand, I'm trying to do the most difficult thing in academia, which is to put a video and a PowerPoint slide on my computer, move it to another computer, and get it to play. So let's see here. So what do we do with all of this? So we actually focus the laser beam down here. This is a focusing lens, and it's very hard to see until I move this around. There's a little tiny white dot there. So I've actually focused this laser down into air, and I've got a very small plasma filament there. So I've actually taken the electrons on the atoms in air and ripped those electrons off. That's the intensity of the laser that I'm looking at. And I'm getting a terahertz generation from that. So let's see here. Yes. Does not work. Oh, wait, there we go.
There we go.
So if you can see the little dot that's not moving inside the circle there, that's actually the plasma filament there. And so I'm actually taking this laser, using the nitrogen in air specifically as the dominant gas, and it's the dominant effect here. And what I'm doing to create the light from all of this, next slide. Get this. So this is a nonlinear material here. I'm mixing these two wavelengths inside this light and using this to generate light. This terahertz light, and so I'm doing a conversion from all of this. There we go. So what am I doing? So I have one photon that's at 800 nanometers, and then that apparatus is also giving me one at twice the photon energy. So I'm doing interference between single and 2 photon absorption and getting terahertz out of all of this. And so what am I looking at a microscopic perspective? I'm creating a plasma there, so I'm coming through with, is any of this going to work here? There we go. I'm coming through with a photon and creating a plasma, so I'm taking that electron off. One of those atoms, it's happening with a photon that's in the blue. The other one, it's going to happen with 2 photons in the red, and it's the interference between the two of them. We'll take some of that energy, which is in the visible, and tune it all the way out to the infrared. For those of you that have taken an electricity and magnetism class, perhaps out of Griffiths or something at that level, this is a susceptibility response for materials that happens at very high intensities. But what we got out of all of this is,
I'm not sure I understand.
Siri getting triggered by my watch. We get out of all of this is part of light that's out here in this far infrared. So this is a sort of an idea of what the spectrum looks like. So we see here in the visible, so we see a fairly narrow region somewhere in the few electron volts per photon energy. And I've been able to take this photon that's out here and tune it out here into the far infrared. And so why am I doing all of this? What's my interest with all of this? So I am somebody that wants to understand the electronic properties of materials. And at these photon energies, these are the sort of things that happen inside of materials. So if I've got a superconductor, those electrons are being bound together by an energy scale that's somewhere in this region of the spectrum. If I want to understand how these carriers move, that's the right energy to talk about electrons moving from atom to atom and all of that. And so what I want to talk today about is, this is going to be one of the experiments where I talk about what's called Landau level spectroscopy. I'll define that in a minute. I'm going to do some ideas of carrier relaxation. I'll talk about that both in terms of the gallium bismuth arsenide, and if I get to the molybdenum disulfide, it'll be something in terms of that. And then this last part I cut this morning because my talk was getting too long and I knew I was limited in time. So let me talk about this material. So 6G, it's not a thing yet, right? We're all talking about fifth generation cell phone networks at this point, and they basically just rolled them out in the last couple of years. So all of this is looking towards new radios for 6G. So I talked about it before. So if you look at the radio that's inside of this that gets me to that cell phone tower, it's silicon germanium. And that's the material that they use for all of this. And they're looking to emit frequencies in the hundreds of megahertz to perhaps a gigahertz, depending upon exactly the speed that you're trying to get out of everything. For a variety of physical reasons, that's not going to work as we scale up higher and higher into frequencies. There's this phenomena in electronics known as the terahertz gap. Once you start to get to several hundred gigahertz to several thousand gigahertz, how many people here have a 300 gigahertz computer processor? How many people have a 3 gigahertz computer processor? That's something you can do, but it's very difficult to go much further beyond all of that because of basically the RC delay of electronics. So you're just not able to get the resistance and capacitance down fast enough to be able to move things fast enough, to be able to get this sort of switch. So what we need to be able to do with all of this now is to develop a new material. So again, most of your electronics in this, and the radio is based on silicon germanium. Right now you're looking at several hundred megahertz. Anyone have a new iPhone 12 or iPhone 13? That's what mine is. So these have, if you look at it, so if you look at the camera hole on that side, there's the power button here, and let's see if you can see this in this picture. There's a gap here. It's going to be very hard to see because it's black on black. That's actually a new antenna on these that works at 30 gigahertz. It's called millimeter wave. And so that's sort of the next generation that cell phone companies are pushing towards. And that's this idea of being able to use 30 gigahertz to 300 gigahertz for all of this for millimeter waves. Why are they doing this? So this is a prediction that's made out of this paper, but this paper's got about 700 citations, so I trust them on all of this, in terms of how much traffic you are generating per month. And the idea over the next 10 years is that's going to go up by about 50 times in terms of the amount of data that you're going to require on a mobile device through a wireless network of some sort. Whether this comes to pass or not is open to question, of course, although these are generally underestimates in terms of the type of growth that are going to be available for all of this. So this is actually it's really hard to see in this light, but there's actually a new antenna on all of this. There's one of them that's wrapped around here, but there's a new antenna that's looking to do 30 to 300 gigahertz in terms of millimeter wave. That they can do with silicon and germanium. And that's available if you bought a phone in the United States, because it has to be a separate radio and a separate approval process for the FCC, so they only ran this through the US system. And that's the last couple of generations of iPhone. And I know some of the Androids do this as well, but I'm an iPhone person. I don't have the experience with all of that. Where's this going to go in 6G? So the proposal for 6G is to have a second band that's available that goes from 275 gigahertz to 3 terahertz. So this is now to the point where they're not going to be able to use existing technology, and we need to develop new materials to do all of this. And the real thing here that's the difficulty is that 3 gigahertz processor that I talk about. You know, Intel can make you a processor at 3 gigahertz, but doing it at 5 gigahertz is possible as long as you've got active cooling and you don't want it on your lap. Otherwise, you're going to cook your lap at a laptop. Anything beyond all of that, heat becomes a massive issue for doing these sorts of electronic applications. On the flip side, for somebody like me that does optical spectroscopy, this is shifting down in wavelength. This is what we know how to do. So what has to happen with all of this in terms of new materials is we need to take a look at this from the optics perspective and figure out how to create materials that will do these sorts of emitters and receivers for next generation applications. And so what we've done with this, and this is in collaboration with Joshua Zeid at the University of Delaware, is it's gallium bismuth arsenide. And the experiment that we're going to be looking at is something called infrared pumped terahertz probe. So I start off with this amplified titanium sapphire beam. This creates 1 pulse every millisecond. And so it has about 7 millijoules in my lab. If I focus it down in air, I'm going to create a plasma. And what we do here is, in a lot of ways, it's a time of flight measurement. I take these 2 pulses, I break them apart. One of them goes through my sample. I make changes to it because of the sample, and the other one comes through as a reference. And so they'll recombine here on my detector. If I've made changes to, for example, the speed of light in the material somehow here, then this path is going to be slightly longer than that path, and I'll see the interference between the 2 of them. And so I actually have a computer-controlled stage here, but it's really, I'm taking these 2 pulses, breaking them apart, and combining them back together again. But if I make changes to my material, I can pick them up because of the slight path length difference. So the speed of light, we all know, is 3 times 10 to the 8th meters per second, or it's 0.3 millimeters per picosecond. And so if I can have very fine level of control over all of this, I can get these very fast processes and materials because I'm looking at how these pulses combine. And then the experiment that I'm going to talk to you, the change that I'm going to do is I'm going to take a piece of all of this, that should actually be in there, something called an optical parametric amplifier, tune the wavelength out of this, and so I'm going to actually photoexcite the sample, change the conductivity of the material, and then study the changes to that using these infrared terahertz pulses. The geometry is called pumped probe from all of this. And what you're going to see here, this is one of the signals, so I'm tracking the electric field here. I see a very fast drop in the electric field over the span of about 2 picoseconds, and then a partial recovery from all of this. What do I get out of all of this? So I created a huge number of electrons in my material, and then I'm watching them go away. And I'm watching how these materials would respond and how quickly I can shuttle electrons around in these materials. So if I wanted to build a radio out of all of it, now I can tell you how quickly I can turn that radio on and off, and how quickly I can start to modulate that, build a radio out of all of this, and then eventually have a cell phone tower in the future out of something like this. So the material, gallium arsenide, let's start with that. So gallium arsenide, as I said, it's this laser that you're looking at here. It's a very common semiconductor. In terms of the manufacture of semiconductors, it's the 2nd most popular semiconductor that people build devices out of, second only to silicon. Anything that's optics related probably starts with gallium arsenide. Silicon does not emit light very well at all. So anytime you want to build something that's emitting light, you would start with gallium arsenide. If you can get away with gallium arsenide, you'll do it with that. If you have to move to another material, you have to move to another material from that. So what we do with this, and this is again with Joshua Zeid at Delaware, he's been able to figure out how to grow the material, and he takes a little bit of the arsenic out and puts a little bit of bismuth into this. And so arsenic is here, and the bismuth is down here. So it's the same chemical valence, but it's a heavier element here. And specifically, the spin orbit coupling of the material is quite a bit larger with all of this. So it's a change in the electronic properties because of the change in the mass here. There's just simply more of it there. It puts strain on the material. And there's also a change in terms of how the electrons couple to magnetic fields. Anytime you go in the periodic table, your spin orbit coupling is relatively weak up here. And as you go down this way, it's going to get stronger and stronger because there are more nuclear moments. There's more in the nucleus itself to create a spin to couple to the electrons.
When you say a little bit, how much is a little bit? What fraction? By a little bit, how much do you mean?
When I said a little bit, which context?
Oh, how much bismuth is replacing?
About 2 to 3% here. So it's very difficult to go well beyond all of that, just because we know theoretically what gallium bismuth should be, but it's actually not a material that's particularly stable from all of this. So we're only talking a couple % tweaking here. So if I took gallium arsenide and I were to look at it, the band gap is about 1.4 eV. It's that wavelength that you're all looking at there. It's about 700 nanometers in wavelength, about 650 to 700, depending upon how you do it. And so what we're doing with adding this bismuth to it is we're trying to take this band gap and make it smaller. So by adding a couple of % of bismuth to all of this, we can take the band gap and we can shrink it down. The next thing that they do is just they actually try and grow a material in this that doesn't want to grow in there, and that's erbium arsenide. So erbium is here in the lanthanides, and arsenic will bond with that fairly easily. It turns out it has about the same structural atom-to-atom spacing lattice constant that gallium arsenide does, so it will grow in there, but it actually doesn't dissolve. So what you end up seeing when you do all of this and you grow this material is, as you're growing it, the erbium arsenide isn't going to spread out easily. It's going to form little puddles. As a matter of fact, on a nanoscale from all of this. So what we end up seeing here is not the erbium incorporating into the lattice as you grow it evenly, but you get little puddles of all of this. And what Dr. Zaid has figured out how to do is to do it very carefully. He can actually do it so you can put the puddles in specific locations of all of this and create an array of nanoislands on all of this in a very controlled fashion from all of this. So he's doing that on a couple of samples, but the technology would scale up to something that we do for this as well. Because you wouldn't need just one chip there, you'd need millions of them. Chemically, what this does is, because the erbium arsenide isn't directly integrated in the gallium arsenide, these appear to be localized states. These appear to be almost like artificial atoms that are placed inside the gallium bismuth arsenide material. And so you end up getting these sort of states here, and they end up splitting the band gap in half. So why is that relevant? So 1.4 eV, this is gallium arsenide, able to shrink it down by adding bismuth in here to make the band gap about an electron volt. The number we want to hit here is 0.8 electron volts. Everything to do with an optical fiber, everything to do with fiber optic communications uses 1550 as the wavelength for all of that. So if I want to use existing technology and existing fiber optics technology, I need to figure out how to create my radio such that it's going to respond to that photon energy. So if all I can do with the bismuth is get the band gap down to 1 electron volt, that's still not enough. I'm actually able to put these states mid-gap such that the peak response is going to be right exactly where an erbium-doped fiber amplifier, which is the laser that people use for all of this, will operate. So this is all materials engineering here. So Joshua has a pretty extensive facility at Delaware where he can grow these materials. We understand by adding more mass, by taking the arsenic out, putting bismuth in there, we understand that that's going to make a band gap generally smaller from all of that. It's also going to add to the magnetic properties of all of this. He's got an extensive history at understanding how to grow erbium arsenide materials in a very controlled fashion and engineer the electronic properties in such a way that we can get out of this what we want. And so he gave me this sample to try and understand whether he actually did what he wanted to do or not. We think we understand the periodic table, we know the trends, we know how to control everything, then you actually have to verify all of it, because every once in a while he's got other ideas than what we have for all of this. So I'm going to be talking a little bit later about an approximation to all of this. And so this is an extended series of states. I'm going to reduce everything down to 3 levels. It's a 4-level system for some of the experiments, but I cut that down a little bit, and I'm only going to talk about 3-level systems and what's called the rate equation approach for all of this. And the goal here is develop a material that we can use for radios, that we can generate terahertz from all of this, and to develop it such that we could use the existing fiber optic network to be able to run next generation cell phone towers. And so that's the longer term goal from all of this. But those are sort of our design parameters from all of this. There's a ton of materials that we could be looking at. This has got a very specific application. They're already using this wavelength in these cell phone towers. They want to take the technology off of an existing cell phone tower and replace it with something else, but they want to do as small of a replacement as possible. So for our analysis for all of these data, and I'll show you some data in a minute, I'm going to use this, what's called a rate equations approach. So I want to understand how, if I take energy and I take an electron that's in my ground state and promote it up to an upper level, how that system is going to relax back down to the ground state. So if I'm up in this higher order level here, I might be able to make a direct transition to the ground state. I might also be able to make an indirect transition down to 2, down to 1. And so I want to be able to understand how to model all of this. And so this is what's called a rate equation approach. So I want to talk about the number of electrons that I have in this top state, and I'm going to look at the time derivative of that. And I'm going to talk about the number of electrons, and so I'm going to look at the rate at which I can populate or depopulate the second state or the first state. So the first approximation you would make would say, well, if I don't have any electrons up in the upper state, I don't have any probability of it dropping down. I won't have any rate down there. If I have a ton of them up there, then there's probably going to be a lot of them dropping down. So I would expect that this rate is going to be proportional to the population that's up here. There we go. So I've got here the rate at which I'm taking electrons out of this level down here, M3, this would be dn dt of n3 is going to be some constant, that's my rate constant k, times n3, and that's going to take an electron from here, drop it down into the lower state. So that's going to be a negative population here. It's going to decrease the population, and then that population is going to appear down here. And then I can do the same thing for this 2-to-1 transition, and then I have my laser that's coming through here that's going to take electrons from here and dump it up, and depending upon the wavelength, I'm either going to populate this 2 state, those are my erbium arsenide states, or I'm going to populate this 3 state, which is my conduction band. So I'm going to either populate, if I come with a high enough photon energy, I'll make that 1 electron gap, 1 electron volt gap here, and be able to populate up in the upper state, and then I'll take some population out of the lower state. Or for other ones, I would be able to, instead of being able to reach this, I might not have the photon energy necessary to do that, so I'm going to put the population in here. So all of these equations here are dn dt is proportional to n. First order differential equations. What's the solution? So I've got the first derivative is equal to some constant times the function itself.
Exponentials.
Exponentials. So what I expect to see from this sort of picture out of everything is all of my populations are going to be some sort of exponential decay. I'll come through with my pump, I'll put everything up in there, and then everything is going to drop down, and the phenomena that I want to pick up are all of these k's that I'm talking about, these rate constants. And so when I do the numerical modeling of all of my data, based on this approach, this is the sort of numerical model that I'll want to fit to everything. So when I do that, my laser pulse itself is not infinitely fast. So there's actually going to be a part of time there where not only am I putting electrons in the upper state, but they're also decaying down at the same time. So I need to actually have a mathematical form that handles all of that. If you go through all of the math out of this, and I won't bore you with it, it turns out it's going to be the error function, the special function, the integral under a bell curve, for the numerical model for all of this. Why is this busy? There we go. So what am I looking at here? So I come through with my optical pulse. I put a whole bunch of carriers inside the material. So for this period of time here, my pulse is coming through the system, and I'm actually populating that upper level, whether it's 2 or 3, it depends upon the wavelength. And I'm populating that level, and so I'm seeing a drop in the transmission of the terahertz pulse as a result. I've got all of these carriers in there, and so instead of the sample allowing the terahertz pulse to propagate through, it's actually reflecting it. So I'm turning this material into a very good mirror in basically a picosecond time frame. Then my pulse is done after about 2 picoseconds. My pulse is all over. And then all of this energy that I've deposited into the system is going to relax out of the system. It's going to thermally migrate itself out to the cryostat that I've got this attached to. And that's going to be this relaxation time. So in terms of the materials parameters that I get out of all of this amplitude here tells me basically how many carriers I've been able to create. So it'll tell me how efficient I am at creating mobile electrons in this material. This sigma here, this pulse width here, that's an instrument response of my system. That's a limit to how fast that I can measure something here, because it's a limit to how fast I can dump the energy into the system. And then the parameter that I want out of all of this is this tau time here, which is if I create this, how quickly can I go before I make this sort of process again? How quickly, once I put the energy into the system, how quickly can it recover from all of that? And then this 4-level systems approach, I can scan these lifetimes, and so as a function of energy here, this is the photon energy, so this is looking at how high up into this ladder that I can propagate here. So 0.5 eV is too small. I'm actually populating a level that doesn't exist. And then at 1 electron volt, I'm able to actually reach up into this level 3 here, this particular material system. And so this is my amplitude, and this is my lifetime. This 0.8 eV, that corresponds to where Joshua thought these erbium arsenide nanoislands should be. So our experimental data actually backed up some of the modeling that he had been doing from all of this, which I can't emphasize enough, never really happens. Usually the numerical modeling is a good approximation, but you're off by a factor of 2 pi, because that's just the way physics works sometimes. So we're actually somewhat astonished that the number, instead of being 0.8 eV, was actually 0.82 eV. That's actually a remarkable agreement. It is a testament to how much he's been working with this and understanding this material. But it actually shows that he's created a robust absorption in this material in exactly the wavelength you would need to have to create a modulator out of all of this. And then you've got a lifetime here that's less than a nanosecond. So now you're looking at something that can be modulated at 1 over a nanosecond or a gigahertz. There's some work that we need to do in order to be able to get this lifetime, which at 600 picoseconds here would be a couple gigahertz. We need to get this up to the 275 to 3 terahertz range. So we need to get these lifetimes down. That actually is data that we feed back to Delaware, and they look at how they're engineering the erbium arsenide nanoisland structure in this material to be able to shorten this particular lifetime. It basically, according to Joshua, it means he needs to change the density of the erbium arsenide nanoislands that he's fabricating, but we don't have that sample yet to be able to test that hypothesis. But this is sort of the feedback mechanism that we get when we're trying to design a material for a particular application. I can tell him what it's actually doing. He understands the design of the material. He can go back and redesign the material, engineer a different material, and then we can iterate back and forth until we can design something that does the particular application that we want. Neither of us is a device grower, so we don't necessarily do the devices on all of this, but we have friends who do. And so this then material would transition over to a group that builds devices out of things. Okay, I want to stop a little bit with that, and I want to talk about now taking an older material, and I'm definitely not going to do the third experiment at this point. Taking an older material, which is gallium arsenide, so that's gallium and arsenic. This is that old material, and I want to understand how to build a quantum computer. How much have you guys been following in the media what they're doing with quantum computers? Google and quantum supremacy, anyone seen all of this type of stuff before? So what is a quantum computer? So if I look at a computer processor, I have a transistor, and it's a 1 or a 0. It's on or it's off. And I chain a whole bunch of them together. Currently it's 64 bits. Change 64 bits together, and I can express numbers to 10 to the 38th power, plus or minus, something along those lines. And I can build an entire computer around a 1 or a 0. So back in 1984, Richard Feynman was asked a question, which is, at that point, you were building transistors, and the minimum feature size was 500 nanometers. They're 2 to 3 nanometers today, so they're substantially smaller than they were back in the mid-1980s. And somebody asked Richard Feynman, as they often did at the time, a real fundamental question, which is the limit to all of this? There's a ton of papers in the 1970s that argue why things can't exist that we have today. So there's a great paper that talks about how you'll never get transistors smaller than 100 nanometers. That it's simply not possible to do all of this. There's a fantastic paper that says everything that we're doing with optical fiber communications is completely impossible. Never say that in a paper. Improbable? Sure. Impossible? Don't say these things. And so they asked Richard Feynman, what's the fundamental limit that you can see for understanding how a transistor worked? And because the man was as brilliant as he was, he came back and said, well, that's kind of a dumb question. I don't want to answer that one. And so he came back, and instead of making this thermodynamic argument about how small you could hold a little chunk of energy in a silicon transistor, he said, well, by the time you get to those limits, where you can talk about how small I can flip energy, you're already into quantum mechanics. And so you're already into this phenomenon here where with quantum mechanics, the switch won't be a 1 or a 0. I wouldn't be able to turn the current on or off. There's going to be this superposition where electrons are allowed to tunnel across gaps. And so he developed in a 3-page paper an entirely new generation of computers called quantum computers. And so these are focused on a unit that's called a qubit, where you've got a system that's in a quantum superposition of 1 and 0. And if you can chain enough of these together, you can build very powerful computers. And so this was a theoretical idea at that point. About four years later, a computational computer scientist by the name of Peter Shor, who was at Bell Labs at the time, which doesn't exist anymore, unfortunately, but existed at the time, developed an entire algorithm for how to use the computer that Feynman had proposed to make encryption that we currently use useless. So encryption as we currently use it is based on the idea that I have a public key that I give to all of you. You can encrypt a message, you can send it to me, but I have to have a private key that's calculated from all of that to decrypt the message. And there's a particular calculation that's necessary to do. It's factoring numbers that are very large into their prime factors that Peter Shor showed how to do much more efficient with a quantum computer than you can do with a classical computer. So if you have something today that's encrypted, the idea is that public key to be able to figure out how to decrypt all of that, it should take the standard computer about a year. That's roughly the time frame of what they consider something to be secure today. And a quantum computer, if you could build it, would basically break it in a day. So everything that we're doing with encryption, every time you put your credit card number into a web browser and send it over to someone else and use that encryption to keep somebody else from stealing your credit card number, would be completely dismantled from all of this. And Google is doing this right now. Google has something they call a quantum computer. There's a paper about a year ago in Quantum Supremacy where they used a quantum computer based on all of this that they've developed. Part of it's done in Austin, some of it's done in Silicon Valley, where they've done a particular calculation, not the Shor's algorithm yet. They've done a particular calculation on a quantum computer in about 2 hours, and the estimate on an Intel processor is it would take about 3 years. And so there's this great efficiency, and there's this number of problems that could happen in custom designed quantum computers that would enhance our ability to do computation. Now, these are not things that are going to be in your pocket. These are things that currently function very near absolute zero. So you need liquid helium-3, you need an elution refrigerator, you need all of this infrastructure to do this. So this is not something you're going to be buying in the next 10 years. When you buy them in the next 10 years, laugh at me for making this. But for right now, it does not appear that this is something you need. But this is something that a federal government research facility could have. This is something that a big university could have. These are sorts of things that people are already starting to talk to do with all of this. So what are we doing? So we're trying to understand from a materials perspective how to do all of this. And so the technique that we use is called cyclotron resonance spectroscopy. So I have a two-dimensional layer here. So what that means in a semiconductor, is it de Broglie wavelength? How many people know what I talk about? So that you're talking about the wavelength of an electron. So I'm talking about a semiconductor layer here that's on the order of a de Broglie wavelength. So in this dimension, electrons can't move. So the electron can move up and down, it can move in and out of the board, but in this direction it's basically confined there. And if I apply a magnetic field to all of this, then classically what am I going to be doing? So all of these electrons are going to be tracing out these circular orbits because they're going to be following the magnetic field lines and tracing out these circular orbits from all of this. And in quantum mechanics, I'm not allowed to do just any circular orbit. The circumference of my circle has to be an even number of de Broglie wavelengths. So I'm only allowed to have certain radii from all of this because I've essentially got some distance there, and the circumference has to be n times that distance. So I would get a spectrum from all of this that ends up looking very much like a series of levels. And relevant to what we do, this is my 0 in a computer, and that would be my 1. So that would be my ground state and my next state up from all of this. And so this has been done a number of times before. This is sort of a plot of people that have done this sort of cyclotron resonance spectroscopy. People started doing this in 2D systems back in the 1980s up to the 1990s. What I've got plotted here is this axis here is something called the mobility. It tells you how pure the semiconductor is. And this basically tells you how many carriers there are in the semiconductor. And so in very poor quality materials, people were doing this for a number of years, but people know how to grow gallium arsenide extremely well. And what we've been able to do now is to be able to look at higher and higher mobilities. Currently, kind of the highest quality samples are somewhere in this 10 to the 7th region there. So that's looking at materials there where there are very few defects, there are very few dislocations. It's an extremely high quality material. I'm able to put an electron into some sort of superposition state and it's going to stay there for a long period of time, so-called coherence time. I'll just get through some of this because I want to get at least the results before you cut me off on all of this. So what we do from all of this is we take a terahertz pulse, we send it through this gallium arsenide two-dimensional system, and what you're seeing here, this ringing here, that's looking at this cyclotron resonance. So I come through with a pulse, I create this two-level system, and what you're looking at here is that system falling apart on its own, right? So I put something into my computer processor, and I want to run a series of calculations on it. If the computer loses power, I lose all of that information from all of this. So this is the same equivalent to all of that. If I were to create a quantum computer and I were to create some sort of signal that I want to do calculations on, what this is measuring is how quickly will the computer forget on its own. This is its amnesia to a certain degree here. And I want to understand this decoherence lifetime in these materials. And so this is sort of these lifetimes from all of this. And so I'm looking at a lifetime of about 15 picoseconds in this, which doesn't seem like it's particularly long. But that's actually an extremely long period of time to be able to do these sorts of manipulations. So that would be looking at a quantum computer processor that would be 100 gigahertz on current scales and something like that. So it would be substantially longer, so it would be substantially faster than something that we've got available to us right now. But we'd actually be able to manipulate these materials on those sorts of timescales. I do want to talk about one other thing, so I'm going to skip the rest of this part of the talk and actually talk about the next part of this. And that's the high magnetic field stuff. I do want to talk about that. And this is a paper we've got coming out in the very near future. And I have a lot of pieces here. Let me just cut to the chase here. The mouse is not working very well. Okay, so the other work that we do, this is in collaboration with the National High Magnetic Field Lab in Tallahassee, Florida. How many of you have ever had an MRI done? Okay, so they stick you in the middle of a superconducting magnet there. It's an niobium germanium superconducting magnet. Have to clear all the metal out of your pockets, otherwise the metal will be onto the magnet as well. Typically, depending upon the resolution of the instrument that you were put in, that's a magnetic field on the order of 1 to 2 Tesla. High-res ones tend to be 2 Tesla. It just depends on what medically was being done. The standard ones are about 1 Tesla, but if for some reason you had some specific phenomenon, maybe it's a 2 Tesla magnet. So this is in Tallahassee. This is the National High Magnetic Field Lab. This is a federal research facility. It's affiliated with Florida State University that looks at high magnetic fields. This is a 25 Tesla magnet. So this is a substantially larger magnetic field than what you're used to dealing with. So the facility, this is the 25 Tesla that we work at. If I walk up to all of this, my head's somewhere right around that yellow sign. So this is a magnet here. It's about the size of an automobile. We use this on a regular basis. This is actually a user facility, so we actually have to apply to work on all of this, but we can look at materials in 25 Tesla, and we're trying to understand the same sorts of coherence properties that I was talking about before, but under very high magnetic fields. In order to sustain 25 Tesla, this is a fully resistive magnet, so this is made out of copper coils, and they just drive a ton of current through all of this. It's actually 34 megawatts of electrical power and 6 kiloamps of current. In order to be able to run through all of this. These green cables that you can see here, about this big around, there's 8 of them going in and 8 of them coming out. That's all of the current that's going into this particular facility. The electricity bill is about $22,000 a week. I don't pay that. Taxpayers pay that one. I jokingly, the director of the lab is a friend of mine. I jokingly asked him how much his electric bill was every month, and he asked how much my house was worth. And at that point, his electric bill, that was before all of the prices have gone up with inflation, but at that point, his electric bill was $480,000 a month, just to run this facility. So what we do with all of this is if you can see here, there's an opening in the side of this. There's an optical window that's about this large. So the same type of optical spectroscopy that I was just talking about, we can actually propagate through the side windows of this. And so this is a new thing in terms of being able to look at high magnetic fields. Most of the other magnets at this facility, there's a 45 Tesla magnet there. It's 2 stories tall. Your experiment, it's 19 millimeter diameter hole in the top of the magnet and 1 meter below the platform. Everything's got to go in and out of that. So you can do an entire experiment down to basically a small pipe. This is actually something where you can actually transmit light through the middle of all of it in 25 Tesla. And the material that we look at here is molybdenum disulfide. So that's molybdenum and sulfur. This grows very different than most materials. So specifically, what is graphite? Carbon, right? So you get carbon basically on a chicken wire platform, and then you get sheets of carbon stacked on top of each other. But the carbon has chemical bonds inside the chicken wire sheets, but then there's weak van der Waals bonds in between them. So if you're using pencil, you peel off several layers and you deposit them down. So you get these sort of mono layers, single atomic layer thick of carbon atoms that are weakly bonded to their neighbors, and you get this either a lubricant, it's used a lot of times for high energy lubricant, or as a pencil if you want to write it all off. Molybdenum disulfide grows the same way. It grows coordinated in the layer, molybdenum and sulfur. It's not flat like the graphite model layer is. There's a little bit of structure to all of it. The chemical bonds have some angles to them, but they basically grow in these mono layers, and then they grow in these stacks of all of that. So the interesting thing about MOS2 versus graphite is it's a semiconductor. Graphite's a semi-metal, so you're never going to be able to build a transistor out of it because you need a band gap to build a transistor. With MOS2, it's a semiconductor. You could talk about building transistors, and then they're literally 1 atom thick. They're as small as they possibly can be from all of this. And so what we wanted to do with all of this, and I know I need to be quiet so we'll be done with all of this, is we wanted to look at, let's get through all of this, what happens to these materials as a function of magnetic field. And so what we ended up doing with all of this is the same sort of pump probe experiment that I discussed, where we actually photoexcite the sample, and this is in high magnetic field, and take a look at the transmission from all of this. And we see this very steep drop off around 17 Tesla. And what we've been able to do with all of this is, if I've got these two monolayer sheets, I'm using the magnetic field and I'm actually torquing the various sheets. And I'm actually using the magnetic field to twist these layers amongst each other. And it turns out there's a very efficient process that kicks in at 17 Tesla where I can control the electronic properties of these. So you're not going to have a 17 Tesla device, but this suggests going back and making these materials with one of these, with some of these twist angles on there, and starting to use the twist angle from layer to layer to control the electronic properties of materials, which is a new phenomenon in materials. So let me skip through the rest of that. I did want to put that up. This sometimes works and sometimes doesn't work. So let me get at least to the end. Conclusions. So we've been able to develop erbium arsenide, gallium bismuth arsenide into a material that we think has some applications for 6G. We've been able to show that we're able to use this cyclotron resonance spectroscopy to understand how to create coherence in gallium arsenide systems. And with this MOS2, it's starting to talk about engineering materials, but actually using the twist angle between materials for engineering properties of materials. Let me thank the people behind all of this. So my graduate students are the ones that do all the work. They just give the talks anymore. They don't let me touch anything anymore, which is probably a smart move. The MOS2 work is Ashlyn Birch. She's now a staff member at Sandia National Labs. That was her PhD project, and it's also Mr. Tracy Hastings. It's also part of his PhD project. Everything that I'm doing with the gallium bismuth arsenide is my current group. Robbie Vuklich, Mohan Giri, and Michelle Caldwell at Baylor. And then the 2D systems is my former graduate student, Jeremy Curtis, who now works for a company in Huntsville. And then some of this was some postdocs of mine, both Biplab Barman, who's at Michigan, and Tenzin Norden, who's now at Los Alamos. And I have a mess of collaborators between Los Alamos, Central Florida, South Florida, Florida State, lots of Florida in there, Sandia, and Los Alamos again. And funding, National Science Foundation, and the Department of Energy. With that, I have a little bit of time for questions, but I don't think I have that much.
Yeah, we've got some minutes for questions. So questions?
Thank you.
Go ahead.
Yeah.
I have one question. I noticed that when you were talking about the doping, the materials, I noticed that the encinum is lanthanide. Is that radioactive?
No. So the top column here, for the most part, is not. The bottom one would be bad news.
Okay.
Yeah. So most everything you've got down here, thorium and uranium. Actually, strangely enough, thorium is more difficult to use than uranium. But then everything after that would be particularly dangerous to use. There's a really famous example of my former coworkers at Los Alamos. They created a new superconductor that would be fantastic to build stuff out. It just happened to be plutonium, cobalt, gallium-5. So the guy that wrote the paper was hilarious because there's this really great description about how great the material is, except for the obvious toxicity of the material. 5 micrograms of plutonium is immediately fatal, so it's not even close. So, but yeah, nothing in there is radioactive per se.
Okay.
In erbium, every fiber laser involved in communications uses erbium. It's a very common element.
Okay.
Despite the fact they call them rare earths.
Other questions for our speaker? If you've got more questions, our speaker will be here for a few minutes.
Yeah.
Otherwise, be happy to join us for lunch in the Joyce Room of the Corner Cafe. And we'll see you all again next week.
Thanks, everyone.
One more time.